Now let's look at two other interesting cases. The case in which we terminate our line with an impedance which is greater than its own characteristic impedance, in our case 100 ohms, and the case in which we terminate the line with an impedance which is lower than its characteristic impedance, in this case 25 ohms. So let's start with the 100 ohm case. When you terminate the line with an impedance which is greater than its own characteristic impedance, you are effectively getting a similar thing to what you get with an open circuit, but much milder. And we have seen this in the manual. What I mean by that is that some of the voltage pulse will be reflected with the same polarity as the incident pulse. But of course, unlike the case of the open circuit, it will not be reflected in its entirety, only part of it will be reflected. And we can see this very clearly here. Only a fraction, about a third, of the incident pulse gets reflected and comes back. Now, yet again, because of the pulse width and the length of the line, and because the pulse width is shorter than the time it takes for the pulse to go to the end of the line and come back, by the time the reflected pulse comes back, the incident pulse is no longer there. However, we can yet again open the tuner and we can take a look at what happens as we increase or decrease the length of the line or the width of the pulse. So, for example, if we decrease the length of the line, we see the reflected pulse coming back towards the incident one, because of course it takes less time for the round trip of the reflected pulse. And then as we increase the length of the line, the opposite happens. Now, if we increase the pulse width, we will get to a point where, as before, we're effectively getting the voltage step effect. And you can see that after the voltage pulse has reached the end of the line and has been reflected, we're not getting a doubling in voltage as in the case of the open circuit, but we're getting an increase in voltage which is proportional to the mismatch between the characteristic impedance of the line and the terminating impedance that we put in there. So yet again, we can see that if we get an increase in voltage, then the impedance we're terminating the line in is actually greater than the characteristic impedance of the line, whereas, as we'll see in a moment, if we use an impedance to terminate the line which is lower than the characteristic impedance of the line, we'll see a decrease in voltage. So let us now look at the case where we are terminating the line with an impedance which is lower than the characteristic impedance of the line, in this case 25 ohms. This again resembles to some extent the case of a short-circuited line, in that the reflected voltage pulse has opposite polarity to the incident one. But of course, unlike the short-circuited case, the amplitude of the reflected voltage is not the same as the amplitude of the incident one, since only part of it gets reflected. This is about a third of the incident voltage that gets reflected in this case. The amplitude of the reflected voltage, of course, is proportional to the mismatch between the terminating impedance and the characteristic impedance of the line. Again, we can look at the round trip from this graph and we can work out the length of the line, and also depending on the width of the pulse and the length of the line, our graph will change. So if we open the tuner yet again, we can decrease the length of the line and see incident and reflected pulses getting closer, or we can increase the length of the line and see them getting further apart. Also, we can increase the pulse width, and we can see that there comes a point where the incident and reflected voltages overlap. And as we carry on increasing the width of the pulse, you can see we're getting a voltage step effect. So what's happening here is that at the 1 nanosecond stamp, the reflected voltage comes back. This has opposite polarity to the incident voltage, but not the same amplitude, so it causes a drop in voltage. And this drop is proportional to the mismatch between the characteristic impedance of the line and the terminating impedance. So yet again, we can work out what's happening at the end of the line just by looking at the superposition of incident and reflected voltages on the line. This is an extremely useful technique called time domain reflectometry, and there are other terminations that can be worked out quite easily by looking at the shape of this type of graph, for example capacitors and inductors. but we will not be looking at those here. It is also great that we are able to simulate this technique with the Microwave Office simulator, and the simulation file will be available to you to download, so you can play around with it as you wish.